Okay, let's look at three quick examples of doing calculations with index of refraction, Snell's law, and total internal reflection. First one, we'll start with index of refraction. If we know that diamond has an index of refraction of 2.42, we can figure out how fast light travels in diamond. So our equation is n equals c over v. Since we're trying to find how fast, we can rearrange this to solve for velocity, and we get c over n. C is just the speed of light in vacuum, our good old friend, 3 times 10 to the 8th. And then we're going to divide that by 2.42, and that's all there is to it. Throw that in your calculator, and you get approximately 1.42 times 10 to the 8th. Now, there were no units here, but there were units on this guy, so we do have units here, which we want because we're trying to find the velocity. So it is still pretty quick, but a bit slower than in air or in vacuum. And one of the other things this high index of refraction does is it means you have a small critical angle. And if your critical angle is small, that means light coming from inside a diamond trying to get out has to hit it almost perpendicular to the surface before it escapes. So most light going in gets trapped for a while, and then when it comes out, you see a lot of it. And so that's one of the reasons why diamonds are so brilliant to look at. Okay, moving right along, a beam of light coming from underwater, an underwater spotlight, and I'm really bad at drawing straight lines lately. Okay, we have a light shining here, the air goes into the air, water here, air here, and when it goes to air, air is going to be faster, so it's going to bend toward the normal. Didn't draw that all that well. Let's get rid of this half. Do it something like this. A little bit better there. Okay, and we're given the angle at which it exits the water. So this angle here is 57.4 degrees, this guy here. And we want to know the angle here, the incident angle at which it left the water. So we're going to use Snell's law for this, which is n1 sine theta 1 equals n2 sine theta 2. And it doesn't really matter which one you plug in on which side, but I tend to have where the light was coming from, I tend to plug that in on the one side. Okay, so for water, n is 1.33. Theta is what we're trying to find. N2 is air, so we're just going to use 1, even though it's 1.0003. And then we've got sine of theta 2, which was 57.4. Okay, so we just have to solve this guy for theta. We can divide the 1.33, both sides by that. So that goes to 1, and then if we take the arc sine, then we're going to have theta 1 equals arc sine of 57.4 divided by 1.33. That whole thing goes into the arc sine, and that works out to be just about 39.3 degrees. Oh, and look at that, I screwed up with my initial description. You guys should have stopped me. So as our barrel is rolling out to the air, it goes faster, so it tilts the other way. So let's go ahead and erase this one more time. So it actually tilts away from the normal, so we're going to say it started nice and close to the normal and tilted away from it because we want this angle here to be less. So always kind of check your answer, make sure that you thought through things correctly or needed to correct things. Alright, one last one here. Critical angle for a certain liquid air surface is 43.9. What is the index of refraction of the liquid? So we're going to assume that the light is going from the liquid to the air. So we want to find the index of refraction of the liquid. We're not going to have some liquid with an index of refraction less than air. So our equation for critical angle is sine of our critical angle equals n2 over n1. Okay, so if you follow the convention of plugging in for n1 the index of refraction from the material from which you originated, then you'll always put in the larger one down here because that's the only time that you get total internal reflection. Also, sine of an angle always has to come out to be equal to 1 or less than 1, so that's another reason why you need the bigger number on the bottom, otherwise you'll get some imaginary answer or something. Okay, so we're going to plug in the numbers we have here. 43.9. N1 is air, so we're just going to plug in 1. Sorry, N2 is air. And then N1 is what we're solving for. So we can just flip places there, and we get sine of 43.9. Plug that guy into our calculator, and we get an index of refraction, unitless quantity, of 1.44. There you go.